Thank you, Susanna, for the introduction and inviting me, and thank you, Tom, for the wonderful talk. I'm really grateful that I'm going after you because you explained a lot of things that I don't have to cover now, so I can get into some of the things that we're doing with transformer models and talk a bit about that. And that's really what I wanted to share today is sort of what are some of the problems that we're solving and get into the practical level for some context, and then a bit about why we chose to work with transformer models, why we use deep learning as opposed to all of the other approaches out there, and some of the lessons that we've learned just as a startup building a product, getting traction in the market with this technology. So first is why patents? Why did we decide to work with patent data specifically? Three big things. It's very big data, about 140 million patent publications are in the data set that we use. They have a lot of labels on them from humans. It's available in multiple different languages, and it's also very, very dense data. So there's a lot of information inside of it, which poses some unique challenges, but also some exciting opportunities. There's a big impact. We actually, despite being in the patent industry, think that a lot of the patent system is kind of broken today, and there's a lot that can be done better, and believe that there's an opportunity to apply the work that we're doing to create that kind of positive social impact. And finally, big market, always important if you're a startup that you're going after a big market. And patent has about 3 million new patents filed every year. There are something like 14 million patents in force today. Not a cheap thing to file a patent, but also after you file them, they actually cost money to keep. And so there's about $9 billion spent every year just on paying to renew and keep patent rights once you have them. So there's quite a bit of money that goes into this. So what's the problem that we're looking at is using patent data. And our mission is to make patent data easier to work with. So when do you need to use patent data? Well, you use it anytime you want to get a patent, anytime you're launching a product, to make sure that you're not infringing on other people's patents. If you're involved in any kind of negotiation, litigation, licensing, buying and selling, you need to go and look at patent data and analyze it. If you want to think about those renewal fees, maybe the patent's not worth keeping anymore, you have to go look at the data, and you have to look at other patents and sort of make a judgment call. And anytime you're gathering business and technical intelligence. And so you can see, just as an example on the right here, is something called an international search report, which you would get from a patent office if you applied for an international patent. And there's a whole bunch of information here that they've gone and done different research to look at patents, analyze them, and then report back on what's found. So today, the way that most patent information is used is pretty much through a process of, first you go to a database, you search for patents to find things that are relevant to whatever your business objective is. Then you need to take that data set, the search hits you get, go through that kind of one by one to make sure that it's relevant to what you're doing, to kind of understand it. And then finally, you get some insights out of it. So we can kind of break this down into tasks that, basically you have an information retrieval task, you have a classification kind of a task, and then you have some analysis and reporting. And for better or for worse, today, this is very, very manual. The primary tool for information retrieval in this industry is still Boolean logic queries. If you've ever done kind of like scientific literature research and access one of these, academic literature databases at a university, it's very similar to those kinds of interfaces, very complex. You have to specify a lot of the logic, combine a lot of keywords, very different from a Google search. And then manual review, just going through them one by one. And after you've gone through the data set, you have to actually go through it again for the more detailed review. And the reason for this is the Boolean logic queries are pretty noisy. They tend to be optimized to not miss things as opposed to be precise to find one good thing. And so you have like 98, 99% noise. It's not uncommon to read 500 patents and only end up having 3 in your final report. So very time consuming to read through all of this. So some of the challenges then in applying NLP to patents, starting first with challenges to people, is it's very highly skilled work, which means that it's both expensive and time consuming, as well as easy to bottleneck. You need to understand patents, you need to understand technology as well. And so it's a difficult thing to do, and you need to know how to create these queries. A lot of the assessment of results is subjective. So there's not like a clear ground truth that you can apply against, and that always is going to make the automation side much harder, as well as the evaluation side. And people get tired. We make mistakes, we have bad days, especially, if you imagine reading 500 patents and most of them are not relevant, you might get a little bored, make a mistake along the way. And finally, it's very prone to kind of failing silently, where you don't know if you haven't found something. So despite best efforts, there are things that are missed. This happens all the time, and it is a very regular thing in the world to lose a patent right because somebody else finds something and basically appeals and says you never should have gotten that patent to begin with, and then you've lost the patent that you thought you had. On the NLP side, some of the unique challenges here are that it's a very large vocabulary, very specific technical language. There are often a lot of synonyms, as well as those synonyms then having different meanings in different contexts. So context is really, really important in a patent. Words like cell can mean many different things. And so the context is critical to knowing, is it a battery? Is it about medical, et cetera? The documents themselves are very, very long. And one of the challenges with neural networks and with deep learning is that despite having a lot of compute power, very, very long documents are still difficult. There are still challenges with how to work with that. And on top of being long, the documents are also dense. So unlike social media posts or a news article, we aren't looking at 2 or 3 concepts. There could easily be 10 or 15, and they're all very interrelated. And finally, it is a very big corpus, as I said, 140 million documents, but it is also very sparse because the nature of technology, there's many different technologies out there, and as you go into each one in a very detailed view, it can get very specific, and especially the newest technology is by definition new, so there's not a lot of similar patents. So a lot of the applications that we're looking at are really working on the cutting edge, where there's not a whole lot of similar documents to base our decisions off of. So that kind of brings us to why deep learning. And essentially what we see as the main opportunities are some of the things that Tom touched on: transfer learning, having large language models available to sort of kickstart things and then being able to fine tune on them. Zero-shot learning is also very promising in this field. And what we see as the opportunity is the information retrieval step, to make that possible to do without needing to write these queries. So that democratizes it, makes it more accessible to others. And then on the actual review process, augmenting what an expert can do to allow them to get through information faster, to find more comprehensively, find results. And then finally, by simplifying a lot of the time and effort that it takes to get to that step, empowering the end user to then go and do more detailed analysis. And that's something that we think is going to remain very much in the hands of experts, kind of to bring what they're finding and apply that to the business context that they work in. So it's a very symbiotic relationship, we think, between the tasks that have to be done and the kind of tools that we can provide to help make that possible. So our goal here is really to build a model that really understands patents very well, that allows you to do a wide variety of different tasks, and then builds on the learnings across those tasks and across users within an organization to get increasingly better for them. So a little bit now about what's working for us. And then I'll talk about some challenges, what's not working. So first, what has worked quite well is that it has generalized very well. So the current model that we use in production, we've tested it across these CPC classes are technical groupings that patents go into, and we've tested it across about 640 total classes, subclasses, and 128 classes. And the comparison shows that generally we do a pretty good job at finding relevant information in these different fields. So that's a good sign. Another thing that's working well is as the state of the art moves forward, and as we learn more from our own research, we're able to build increasingly sophisticated architectures that can do better with our core model. And so I've got here just a graph showing some improvement in performance from version 1, 2, and 3, where version 1 we released in 2018, version 2 was the end of 2019, and version 3 we just recently released. And finally, with some of the fine-tuning and classification, we can show that comparing with our existing embeddings using like a support vector machine, a very basic kind of standard out-of-the-box classifier, we get kind of decent results. These are a little bit better than what you get doing the same thing with like the bag of words. And then doing a fine-tuned model actually gets significantly better results. And by fine-tuning, we can also reduce the number of examples it needs to see to do effective classification. So a lot of the data science side is going quite well for us. Some of the challenges and learnings that we've had are really more on some of the commercialization aspects, and gets a little bit to some of the drawbacks and challenges with the current state of transformers, as powerful as they are. So first, I'll start with kind of this meme. If you haven't seen this one, it's a good one. It is easy to get a little bit lost in the forest and kind of forget the forest for the trees when working on exciting new technology. Ultimately, what we're trying to sell is a product that allows our end users to get their jobs done and to do things that are amazing. And it's not enough really to just give them the product. They don't know necessarily immediately how to use it. And what that kind of gets to is that fundamentally, what we've learned is just that changing behavior is very, very hard. It is not enough to just have numbers about beating state of the art or showing great performance, or even on real cases, benchmarking against, for example, we will sometimes benchmark against the customer's patent activity to help them see and predict ROI. At the end of the day, though, what's really critical is building trust in these kinds of systems and end users. You know, if you're fortunate enough to have a technical end user, that's a little easier because they can interpret things a bit more directly. But if not, they really need observability. And so this is something that we've had to go through many iterations with, figuring out how to take what our model understands and knows and present that information in a way that is useful to a human, but more importantly, allows them to have a kind of conversation with the AI. So that dynamic of that human machine interaction is really, really important. And so what we've really found is that UI UX is king here. And getting that right has actually been probably the hardest part for us, figuring out a way to package up the amazing things that our technology can do into a way that's really easy for users to get value from. And so what I would leave you all with as a bit of advice from at least our learnings is to work on optimizing the machine learning side of things last. We're very fortunate to live in a time where off-the-shelf tools can do amazing things. I will admit that we're biased. We're a happy paying user of Hugging Face and get a lot of value from those kinds of tools. And they do a wonderful job. And that makes it very easy to get something functioning so that you can first focus on the UI and the UX. If you're looking at building a product, if you're looking at doing anything that has to go to an end user that's non-technical, start with that. Get to that prototyping level as fast as you can without having to worry about the machine learning side of it. And it doesn't matter if you know that you can't go to market with sort of the initial results, or if they're not good enough. We thought that was going to be critical for us, that we had to prove that the transformer model approach we were taking would work. But with the benefit of hindsight, I can say that focusing on the UI UX and really iterating on that quickly, first, it's cheaper, it's faster, and you'll learn a lot more. If you're absolutely unable to do that, then at a minimum, what we've learned is invest in the data and the kind of ML ops first. It makes such a difference. It allows you to iterate on the research so much faster, and taking the time to get that right just pays dividends. And probably the biggest challenges for us even today running our application in production really do fall into the data and the ML ops side, because we new patents are published every week from a large number of different sources. We have to bring all of that data together, make sure that it's properly cleaned, and then we also have to run that through our models running inference, and doing that every week in on a startup budget, and in a way that isn't disruptive is not trivial. But also it's high stakes for us, because any kind of disruptions to data or inaccurate data could cause our customers to make very consequential and very painful decisions. So we have a very high requirement to be accurate with what we're doing and have visibility into it, and be able to see it. So even if the stakes aren't quite that high, we definitely regret not investing heavier into the data side earlier. It would have accelerated our ability to do the machine learning later. And so I guess you can think of it very much like factory automation, perhaps unsurprisingly. It doesn't make any sense to optimize your production line before you know what the line looks like. Know what you're building, understand what the outcomes look like, where things fail, what needs to be tweaked, and then at the end of it, you can pour effort into optimizing that and really driving that process. And that has come to be how we see a lot of the machine learning work that we're doing. So thank you all very much for listening.